Welcome everyone. Let me go to the third talk on the same topic. So our last talk contained that field extension. Field extension. Sorry. So let us start by two problems. Question one. So that Q adjoint per Q. That is the set of all the field of all rational. So it is a field extension. Infinite. How to prove this? I remind you what is this thing? These things are actions of polynomials in this. So what is this? This is fraction where the numerator and denominator both come from this thing, polynomial ring. Okay? That is the polynomial in these things. And if you take the fraction, for example, root 2 by root 5, root 2 plus root 3 by 2, root, root 5 plus root 7 by root 3 plus root 2. All of things belongs to there. I think you understand. Okay. So let we assume that is a finite extension, and we will produce some contradiction, try to produce that degree of extension. So that is attaching the square roots of prime. Okay. Suppose it is n, then it is vector space argument. Algebraically dependent over Q. Let Q1 n plus 1 prime numbers. Then there is algebra independent. So there exist coefficients A1, A2 plus 1 belongs to Q such that not all AI equal to 0 with satisfying the equation. Okay, satisfying so we are working on these. So I have to check. Sorry, I have to take square root. let AK be the max of AI such that AI non-zero. Then the above equation is okay. Now this is an absurd condition. Because I mean you can understand, right? For example, particular case, if n equal to 3, then the first three polynomials are 2, 5, sorry, 2, 3, and 5. So a1 root 2 plus a2 root 3 plus a3 root 5, that is 0, is impossible. Because left hand side in LHS, get and mutation in RHS, we get rational marker. So there is a contradiction. Okay, thus second is second one is so that verification. How to show? Again, let us assume degree of extension is finite. Let n, then any n plus 1 elements of u by the set or any set of then any set of algebraically dependent over q. Okay, so I am taking in particular 1 by square algebraically dependent over Q. That means there exists A1, A n plus 1 belongs to Q, not on 0, such that we have I square A n by n plus 1. Okay, so let as previously I will assume that K equal to max of I, AI non-zero, then we have, because after that everything's AK is 0, so I don't need those terms. We have A1 plus dot 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 plus, okay, I'm writing here A1 dot 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 plus AK pi to the power k, that will be A n plus 1, okay. That implies pi satisfies the equation AK x power k, AK minus 1 x k minus 1, 0, 0. It is a contradiction. Why it is a contradiction? Because pi is transcendental. Okay. So what was my proof? Suppose this is n. So I take any n. So any n plus 1 elements of Q pi is algebraic dependent over Q, because it is a vector space theoretic argument that if I take any set of elements whose cardinality is more than the basis, then they will be linearly dependent. So as soon as they become linearly independent, I will get a set of coefficients, okay, such that not all of 0, not everything is 0, such that they will satisfy this. Now, I assumed K to be this thing, which says that the more thing is this, okay, which implies that pi satisfies. So this equation, but pi is transcendental number. So how it is possible? So that is the contradiction here. I think you understand. If there is any problem, please let me know. Okay. Next, we will go to some. We are our target in this first few lectures is going towards that splitting field. Okay, that we will use everywhere later on in whenever you study normal extension, separable extension, splitting field. That splitting field is very important concept where our target is goes to the splitting field. So let us proceed. That is an important proposition. You can do so by yourself. The homomorphism is either 0 or sorry or injective. Okay. So my target is to show if there is any non-trivial field homomorphism, then it will be injective. I is a homomorphism between two fields f and f dash. So I will consider the kernel and show you. Because injective means phi of u 0, that must imply u equal to 0. F dash, let phi not non-zero. Then what is kernel of phi? So, okay. So then there exists u non equal to 0 as that phi of u non-zero. That is the non-zero map. Okay. Now what is kernel of phi? Now let a belongs to kernel. Then phi of k equal to 0. It is 0 of f dash. Huh? So if possible, let k non-zero. Okay. Then and guys, phi of k, take phi both sides. Guys, phi equal phi inverse phi 1. But phi of 1 is 1 of f dash. That means, and phi of k is 0. That means 1 of f dash equal to 0 of f dash. So 1 and 0 different element. That is a contradiction. So k equal to 0, which implies that Okay. Understand the proof? You understood the proof? Just I selected an element, considered the kernel, and proved by contradiction by taking the inverse of this. Next is very important. Next theorem is very important for splitting field. Okay. What is the theorem? So first motivate. Let me motivate. You already know in consider x square plus 1 equal to 0. No solution, irreducible enough. But if we extend R to any field which is C, then in this field that equation has zeros. I minus I. So again in Q, the equation x square plus x square minus 2 equal to 0 has no solution. But if we extend the field to C or extend the field to U root 2, that extension, zeros are there, root 2 and minus root 2. So if you give me a field F and a irreducible polynomial fx, then what can I say about the availability fx in F? So in F, there might be roots, might not be roots. Maybe yes, no. For example, if you give me the field R and give the polynomial x plus 1 equal to 0, then obviously this polynomial has an equation root in R. Okay? But if you give me the polynomial in x square plus 1 equal to 0, then in R, no roots. So if the polynomial has no root, can I extend any field to a bigger field such that in this field, the irreducible polynomial have certainly 0. 0 present hoga hi hoga, to be honest. Is this, does that, can I extend the field or construct a bigger field, or there exists some field so that that phenomenon happens? The answer is yes. Okay. So what is our target? Our target is to suppose we are given a field and a irreducible polynomial coefficients from the field. Our target if to find the roots in some field. So if the roots are already in the field, then we don't need to go anywhere. But if the roots, all roots are not there, our target is to find a bigger field than the given field, so that in the bigger field we can have all elements. Okay. What is the bigger field? So in this theorem, I will just prove the existence of the proof is existence of the bigger about the existence of that field. But that is a confusing. The field might look confusing, but sometime later I will give a beautiful structure of the field. So don't panic. So you understand my motivation, I think. If not, then just kindly pause the video and see this again. And if there is any problem or error that I have made, just let me know in the comment section of the video. So what is the theorem? Let me first state me in the formal form. Let if Px belongs to Fx, usable polynomial. Px belongs to Fx. Okay. Then there is a field extension of F which X is root. Okay. You understand the statement that I need to show? So what is the field? So I am again saying the field might look a bit confusing to you in the first sight, but sometimes later I will actually show that field you already know. What is the field? I mean, you already, that is much a beautiful figure. So, okay. So you are already quotient familiar with the quotient ring and quotient fields. Consider the quotient ring. I will denote it by K, which is actually nothing but Fx modulo Px. Okay. Now observe that Px is irreducible and Fx is a field of ring of polynomials over field. So if we go mod by an irreducible, what will this do? This will give me a field. So why? Because being irreducible means that is a maximal ideal. And R mod M is a field if M is maximal. As Px is irreducible in Fx or reducible over F, it is maximal. Thus, Fx mod Px equal to K is a field. Field. That is a field. My candidate is this field. So I need to show there exists a field. That is a field. That is the field. First, I need to show that Fx mod Px, that is extension. So that contains F. We need to show that first. What that means if it contains K, I need to show. There is projection map. Obviously, there is a projection map. Pi goes to fx to fx. Right. Defined as pi of fx goes to f bar x. This is fx plus px. You know that is a ring homomorphism. Now, if I restrict pi, define the now pi, which is to be defined as restriction of pi in f. This is a map from f to fx to that x. Okay. So that is an extension from f to fx. That is a surjective extension. Surjective homomorphism. So, but a field homomorphism, I proved that here is zero or injective, but it is not zero, so it is injective map. But phi is already injective. Thus, phi is actually an isomorphism. Okay. So see that so the restriction map where I have defined is isomorphic copy. I am sorry. There is not surjective. This is not surjective. Yes. I am sorry. It is not surjective map. So it is a field homomorphism, but it is already injective. Thus, if isomorphic to phi f, which is contained inside K. So if we identify f as phi f, because isomorphic copies preserve isomorphic, there are the isomorphism, so mm, they preserve all properties, ringness, fieldness, everything, algebraic properties, whatever you will take. So if we identify phi, f at phi f, then A contains f. So A is an extension f. Now I show that I need to put, so tens group of px. Okay. See, so in K we denote x as pi x is x bar. Okay. Now, so what happened if I put p of, then what is p of x bar? It is p of x plus px. Now, if I take px as zero, then p of x bar, that is what? That is a n x. Everything will be there, a zero. That means a n x plus px. Okay, sorry for that mistake. So where I was that there, right? Is plus a zero. That means if you break mod px, you will get an x power n plus a n minus n. This is ideal generated by px. Okay. Px. This is this plus not px. This is mod px. So this is px equal to 0 mod px. So it is 0 mod px, which is in the, so in k it is 0. In k it is 0. So I see that what I see, so p of something is 0 bar in k. What is the element? It is x bar. So p has a root in k because the root is x bar. Let me write it properly. Sorry. So p has a root. Okay, so the proof is complete. See the proof. That I think it is okay. So let us proceed. So our next theorem shows that. So I already told you. I already told you that that will be used in the construction of the splitting field. Okay. So but this is not splitting field because I told you that it contains one root. I didn't say you that this might contain all of the roots of px. Okay. So if second thing is that I told that extension k, which is fx mod px, that is an extension of f. Sorry, k is an extension of f. So there is, the extension means there is infinite or finite. If I ask you, what is the answer? So we will find the answer in our next theorem. That is a finite extension. Okay, and finite means the, if I look k as a vector space over f, then what are the bases? Give me, you can ask me, just give me one set of bases, then what could be the possible bases? Next theorem. So now you are familiar with the notations, so, and moreover relaxed over it, so I can continue. Let px belongs to fx be an irreducible polynomial degree n. So that might have a finite degree, okay? And let it is a field. That is a field k equal to this. Let theta or x bar, whatever you can say, you theta or x bar or x, that is x plus px, the image of x plus px or x mod px. Everything is same. Okay. Whatever is this, let that be theta. I am not denoting is this. Then 1 theta theta square n minus 1 is the basis of the vector space uh, x over f. Understand? I need to prove this. Okay, don't worry, I will prove this. So that means if that means degree of what that means that is degree of the extension is is degree of the polynomial px. Okay, and what is k then? K is will exactly look like the linear combinations of the basis elements. So it will be all types of such that element such that a0 to an minus 1 all belongs to. Okay, see, that line is trivial from this. It is a basis and the scalar is this, scalar is this, and this is the basis. So it will be F linear combination. That is fine. Okay. Just look at the statement for some time first. Then I will go to the proof. Actually, you might ask me why I am taking everywhere irreducible polynomial. I might take reducible polynomial, right? For example, I might take product of two polynomials, a polynomial or that can be factored into two or three smaller pieces of polynomials. But ultimately, what you are getting at each term, the ultimately three pieces that will be again irreducible. So you can factorize an polynomial up to the irreducible components. So above irreducible component, we cannot go. So our interest, above irreducible component, how much we can go. Therefore, we are taking irreducible. If you take any family of polynomial, then you might end up again being to the irreducible family. Okay. So let me proceed. Okay. So first, I will show how a thing in the quotient field, a quotient ring in K, I mean K is fx modulo px, will look like. So it is surjective map. So every polynomial has its image. Let ax inside fx. Then, since fx is an UFD, PD is necessary. UFD is not. PD, that means Euclidean domain. So, and perform. So there exist obviously Qx and Rx. Fx such that Ax equal to Px Qx plus Rx, where Rx is either 0 or its degree is less than. But in K, passing through the quotient ring K, will get it is only Rx. They are same because that term is because quotient thing. So that this thing is multiple of Px, so that will absorb here in the equivalence class of 0. 0 or equivalence class of 0, which is 0 bar in the quotient, because it is a multiple of the 0 thing. Px is 0 here in the quotient. So anything multiple with 0 is 0. So that thing is 0. So only survive this thing. The survivor will be this thing. Okay. Okay. So if I start with any polynomial of any degree, I don't know what is the degree of Ax. I will end up being that is equal to being a polynomial that is less than degree n. N means degree of Px. So in K, I will not get any polynomial of degree more than n, degree more than n minus 1. Because n degree polynomial, that will be same case also. P will divide this and end up the remainder will be obviously degree less than this. Because if the coefficient does not match, I can equalize the coefficient by multiple suitable things and adjusting. Okay. So no problem there. So now see, that is not the end. Rx bar is combination of what is in, so in a normal ring. So if A is a ring in AX, that thing, what is the basis of this ring? This is 1x x square x n, as that will continue. Okay, but that will not give me more than in my what is this degree of n minus 1. Huh. That will not give me more than n minus 1 degree polynomial. So their basis will be 1 x bar square up to x n minus 1, because up to this, above this we cannot go. Okay, so their image, the basis of this, the canonical image of the basis will give me the basis of the that quotient over K. So 1 theta square theta n minus 1 basis of F. Oh, sorry, basis of K over F. So I will not say it is a basis. I will first say it is span. Span the vector space A over F. Because linear independence is not established yet. So it is a spanning set. Okay? Spanning set, and I cannot go above the degree of this thing. So 5 to the power n minus 1, only x bar to the power n minus 1 will be there. Now we check their linearly independency. So, for example, if possible, assume that they are not linearly independent. Independent. Okay. So there exist scalars b 0, b n minus 1. Just a minute. Just a minute. Belongs to F such that sorry, not every I equal to 0 with the property plus v1 theta plus 0. That is 0 bar, which will imply that b1, but what is b? sorry, V0, it is V1, it is x plus ideal generated by Px. It is plus dot 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 plus Vn minus 1 x plus ideal generated by Px minus 1. There will be another bracket. That is 0 plus Px. So if you do the calculation, then we can show that V0 plus V1 x plus V2 x square Vn minus 1 x to the power n minus 1 belongs to ideal generated by x. Okay. That means Px divides V0 plus, which is a contradiction. Since degree of Px is n and degree of this polynomial is at most n minus 1. Why at most? Because I don't know what is Bn minus 1. If it is 0, then that degree will reduce. And if it is non-zero, it will remain n minus 1. So obviously a smaller degree polynomial cannot divide a larger degree polynomial. Okay, that is the reason. So why this contradiction arises? Because we assume that they are linearly dependent. So independent. Okay. They are linearly independent. So I showed that they already spans. They spanning set plus linearly independent. That means they are basis. So a basis. Okay. So the degree reduction comes from Euclidean division algorithm. That comes from there. And passing through the cosine tree, we saw that only that number of elements that would survive here. That is the degree, sorry, not number. The degree of elements would be less than equals to n for being survive. So we showed that. So for first of all, this is a ring. Okay, field is far from field is also field, but first of all, it is a ring. So what is the addition and multiplication? That is a corollary. The observation. I will give example, don't worry. the addition in A is natural. A between two polynomials degree less than n is natural. I mean, as you add everywhere x plus x square is x cube, both degrees should be less than equal to less than n. But the implication follows as if fx and gx or theta, I denoted is by a theta according to the book, are friends of k with degree f theta degree of g theta less than n, then f theta g theta will be r theta, and r is the remainder, rx is the remainder. It's divided by px. Right? See, f theta means fx plus px. G theta means gx plus. So f theta g theta by the proper formula of quotient ring, that will be now fx gx is a polynomial. Okay, so we can divide fx gx by px. So by division algorithm, again there will be something like, say, hx plus hx px plus. Okay, let me write here. Such that okay, that means what is f theta g theta? Hx px plus rx plus ideal generated by px. Now this px will absorb this thing. The only thing will be you can look at it from this perspective also. theta is the theta is x mod px. So Rx means that thing. So Rx, you expand Rx in terms of x, and with the each monomial you attach plus px. So that will give you r theta, r in theta. This is clear. Example. So I will give example on next class. So for this, for today, this is enough.